Hello friends, welcome to a lecture on biogeochemical phosphorus cycle. The main objectives of today's presentation are to know about pools and fluxes of phosphorus and to highlight the various processes involved in the cycling of phosphorus. First of all, the introduction of the topic. The phosphorus cycle is the biogeochemical cycle that describes the movement of phosphorus through the lithosphere, hydrosphere and biosphere. Unlike many other biogeochemical cycles, the atmosphere does not play a significant role in the movement of phosphorus because phosphorus and phosphorus-based compounds are usually solids at the typical ranges of temperature and pressure found on Earth. Since soil microorganisms act as sink and sources of available phosphorus in the biogeochemical cycle, however, the major transfer in the global cycle of phosphorus are not driven by microbial reactions. Now, the biological functions of the phosphorus. Phosphorus is an essential nutrient for plants and animals. It forms part of life-sustaining biomolecules. The primary biological importance of phosphates is because they are the components of nucleotides. The helix of DNA is the only possible because of phosphate ester bridge that binds the helix. Besides biomolecules, phosphorus is also found in bones as calcium phosphate, in enamel of mammalian teeth, exoskeleton of insects and phospholipids. Biological productivity is contingent upon the availability of phosphorus to these simple organisms that constitute the base of food web in both terrestrial and aquatic systems. Recent studies indicated that phosphorus is the limiting nutrient for cyanobacteria, algae and dinoflagellates, affecting the phenomenon such as red tide. Now, the ecological functions. Over time, geologic processes can bring ocean sediment to land, followed by weathering. Plants absorb phosphates from the soil and then bind the phosphate into organic compounds. The plants may then be consumed by herbivores, which in turn may be consumed by carnivores. After death, the animals or plant decays and the phosphates are returned to the soil. Runoff may carry them back to the ocean or they may be reincorporated into rock. Phosphates move quickly through plants and animals. However, the processes that move them through the soil or ocean are very slow, making the phosphorus cycle overall one of the slowest biogeochemical cycles. Now, coming to the reservoirs, the rock and their deposits formed in the geological past constitute the major reservoir of phosphorus. The land biota contain only a minute amount of phosphorus, about 2600 Tgs compared to 96,000 Tg of soil or 19,000 Tg of mineable rocks. Similarly, although total dissolved phosphorus in the oceans is 80,000 Tgs, marine biota contain only 50 to 120 Tgs of phosphorus. Further, although land plants have 20 to 50 times as much as phosphorus as marine biomass, the cycle only 200 Tgs of phosphorus per year compared to 600 to 1000 Tgs per year cycled by marine biota. As a result of erosion of soils and rocks or leaching of dissolved forms, phosphates are released into rivers and lakes, etc. Some of them are precipitated in lake sediments, while the majority escapes into the sea, where part of it is dissolved in shallow sediments and part of it is lost to deep sediments. As organisms die and sink to lower levels, surface water becomes depleted of phosphorus supplies, but upwelling of deep waters returns some phosphorus to the surface. Through the uplifting of sediments and the harvest of fish from sea, the phosphorus returns from sea to land. Seabirds, by depositing their fecal material on land, also contribute significantly to the return of phosphorus to the cycle. Now the forms of the phosphorus. The primary mineral form of phosphorus is rock phosphate or apatite. In terrestrial systems, phosphorus resides in three pools, that is bedrock, soil and living organisms. Weathering of continental bedrock is the principal source of phosphorus to the soils that support continental vegetation. Phosphorus is weathered from bedrock by dissolution of phosphorus bearing minerals such as apatite, the most abundant primary phosphorus mineral in crustal rocks. Weathering reactions are driven by exposure of minerals to naturally occurring acids derived mainly from microbial activity. Although widely distributed in nature, phosphorus is not found by itself in elemental form, as elemental form of phosphorus is extremely reactive and will combine with oxygen when exposed to the air. In natural systems like soil and water, phosphorus exists as phosphate, a chemical form in which each phosphorus atom is surrounded by 4 oxygen atoms. Orthophosphate. The simplest phosphate has the chemical formula PO4 3 negative. In water, orthophosphate mostly exists as H2PO4 negative at a pH below 7.2, that is in acidic conditions, or as HPO4 2 negative when pH is above 7.2 in alkaline conditions. In soils, phosphorus may exist in many different forms. In practical terms, however, phosphorus in soils can be thought of existing in 3 pools: solution phosphorus, active phosphorus and fixed phosphorus. The solution phosphorus pool is very small and represent only a fraction of a pound of phosphorus per acre. The solution phosphorus is usually in the orthophosphate form, but small amount of organic phosphorus may exist as well. The solution phosphorus pool is important because it is the pool from which plants take up phosphorus and is the only pool that has any measurable mobility. The active phosphorus is the phosphorus in the solid phase, which is relatively easily released to the soil solution. As plants take up phosphate, the concentration of phosphate in solution is decreased and some phosphate from the active phosphorus pool is released. Because the solution phosphorus pool is very small, the active phosphorus pool is the main source of available phosphorus for crops. The ability of active phosphorus pool to replenish the soil solution pool in a soil is what makes it fertile with respect to phosphate. The fixed phosphorus pool of phosphate contains inorganic phosphate compounds that are very insoluble and organic compounds that are resistant to mineralization by microorganisms in the soil. Phosphate in this pool may remain in soils for years without being made available to plants and may have very little impact on the fertility of a soil. Phosphorus is affected by both biological and chemical reactions, and accordingly phosphorus cycle is divided into geochemical subcycle and biological subcycle. First, the geochemical subcycle. In geochemical phosphorus subcycle, orthophosphate is solubilized from primary and secondary minerals by chemical and biochemical weathering process. Dissolution of these compounds in the soil solution or solubilization through microbially produced organic acids releases orthophosphate to the soil solution for plant and microbial uptake. In biological subcycle, orthophosphate can be taken up by plants or immobilized into microbial biomass. As plant residues and animal wastes are returned to the soil, the organic phosphorus may be directly incorporated into stable humus mineralized to orthophosphate or immobilized into microbial biomass. Biomass phosphorus is subjected to incorporation in humic substances and mineralization and immobilization reactions. Hence, phosphorus availability is controlled by mineralization and immobilization through the organic fraction, solubilization and precipitation of phosphate in inorganic forms. First, the mineralization and immobilization of phosphorus. Phosphate is taken up by plants from soils, utilized by animals that consume plants and returned to the soil as organic residues decay in soils. Much of the phosphate used by living organisms becomes incorporated into organic compounds. When plant materials are returned to the soil, this organic phosphate is slowly released as inorganic phosphate or is incorporated into more stable organic materials and become part of the soil organic matter. The release of inorganic phosphate from organic phosphate is called mineralization and is caused by microorganisms by breaking down organic compounds. Phosphorus mineralization is an enzymatic process, as a group of enzymes involved called phosphatases catalyze a variety of reactions that release phosphate from organic phosphorus compounds to the soil solution. Phosphates are released by microorganisms extracellularly into the soil solution to catalyze these hydrolytic mineralization reactions. Once phosphorus is mineralized, it can be taken up by plants or immobilized back into microbial cells, or it can form insoluble inorganic complexes. Immobilization is affected by the carbon to phosphorus ratio of organic material being decomposed and the amount of the available phosphorus in soil solution. If insufficient phosphorus is available in the residue for assimilation of the added carbon, then inorganic phosphorus from soil solution must be used and net immobilization occurs. Conversely, if more phosphorus is present in the residue than is needed for carbon assimilation, net mineralization of orthophosphate occurs. Generally, Cp ratio less than 200:1 results in mineralization and Cp ratio greater than 300:1 results in immobilization. In addition to phosphorus content of residues, other soils and environmental variables like pH, temperature, aeration and soil moisture affect microbial activity and phosphorus mineralization. The element that is most limiting controls the overall mineralization of a residue. Now, the solubilization of inorganic phosphorus. Inorganic phosphorus minerals are generally found as aluminum and iron phosphates in acidic soils, while calcium phosphates dominate in alkaline soils. These slightly soluble compounds provide orthophosphate to soil solution to the extent allowed by solubility of compound. Orthophosphate is supplied to roots primarily by diffusion. Thus, chemical equilibrium between orthophosphate adsorbed orthophosphate and inorganic phosphate minerals are important in supplying phosphorus to plants and microorganisms. As phosphorus is taken up, it is replenished from these resources. Plant roots and microorganisms can enhance the dissolution of phosphate compounds by the release of carbon dioxide and organic acids to the soil solution. Carbonic acid can promote the acid dissolution of calcium and magnesium phosphate compounds. One group of organisms in this regard is mycorrhizal fungi, form symbiosis with plant roots and enhance the uptake of phosphorus and other nutrients. Important organisms active in solubilization of inorganic phosphate include both bacteria and fungi, such as species of Bacillus, Pseudomonas, Micrococcus, Flavobacterium, Aspergillus, Penicillium, Fusarium and others. The enzymes involved in cleaving phosphate from organic phosphorus compounds are collectively known as phosphatases. These enzymes show a broad range of substrate specificity and are grouped into two groups, alkaline and acidic, based on their pH optima. So, microorganisms are known to bring about a number of transformations of this element. These include altering its solubility, mineralization of organic phosphate compounds into inorganic phosphates, oxidation and reduction of phosphorus compounds. Now, the environmental aspects of phosphorus cycling. Phosphorus can cause environmental damage if applied in excess to the soil. Phosphorus is the most limiting nutrient for primary productivity in many ecosystems, particularly aquatic ecosystems. If a large amount of phosphorus is applied to soil, it may move to surface waters with runoff water and with eroded soil particles that bind phosphorus. The major consequence is a process called eutrophication. If phosphorus is the limiting nutrient in the pond, excess phosphorus addition can result in rapid growth of algae in water. This algal bloom is often noticed as green scum or film on water surface. As algae die, they settle to the bottom where bacterial decomposition of the nutrient-rich alga occurs. The decomposition of the alga results in oxygen depletion. If the process continues, the lake slowly becomes aerobic, resulting in poor environment for many forms of aquatic life. In the end, phosphorus cycle can be summarized as: lithosphere is the major reservoir of phosphorus. From rocks, phosphorus is released by weathering. After weathering, the released phosphorus is transported to soil by wind or waters as inorganic phosphate. Inorganic phosphate is absorbed and assimilated by plants. In most soils, the amount of available phosphorus is about 0.01% of the total phosphorus in soil. From the plants, phosphorus moves through the food chain in organic form. The debris of plants, animals and microorganisms return organic phosphates. The dead organic matter is acted upon by phosphatizing bacteria to release inorganic phosphorus from bound organic form. Phosphorus is lost as runoff water into the deep sea and ocean sediments. Phosphorus is returned from shallow marine deposits in fish harvest and fecal deposits of fish-eating birds and geological uplift. Turnover of organic phosphorus occurs due to phosphatase activity associated with root activity and microbial populations. Hope you have understood the various aspects of phosphorus cycle.